In this lesson, we're looking at how computers represent images. So we need to know that the smallest element of an image is called a pixel. We need to know that each pixel has a specific color represented by a specific binary code. And we need to know that all of the pixels form an image which is known as a bitmap. And hopefully all of that's going to become very, very clear. So here I've got an image which I have blown up, not literally, of course. And we can see that this image is made up of all these little dots, and these dots are known as pixels, or picture elements, right? So pixel is short for picture elements, which I know is a bit weird because we've got an X in the middle, otherwise it would be like pickle. So I think pixel is just computer scientists having a little bit of fun, that's why it's called pixel. So a pixel is the smallest addressable element within a picture. So if you think of like your massive TV screen or a mobile phone screen, right, it's possible for one pixel to change at a time, which is quite amazing when you consider there's over 1 million pixels on a typical screen. So to make this clear, let's start looking at black and white images. So we need to know that the pixel is represented in a black and white image by a 0 or a 1. Right, so here's a 5x5 image for demonstration. Now, some of you are probably already saying, well, black and white are shades and not colours, but don't worry. Just for the purpose of computer science, just think of them as colours. Okay. Now, this is going to be a 1-bit image, which means that we're going to use 1 binary digit to represent each pixel. So you can probably work out from that that one of these colours is going to be 0 and the other one is going to be 1. But for the purpose of this demo, we are using 1 for white and 0 for black. So this is going to be 1. So from left to right, top to bottom, this is going to be 1, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. I think that was enough ones, but you get the idea. So it's a 1-bit image because we're using 1 binary bit per pixel. So what we can do is to demonstrate that is we've got a little tool here I can use, and this one it's the other way around. It's 0 for white and 1 for black, just to confuse everyone. And right, what do you think of my smiley face? It's not very high resolution, is it? I.e. not many pixels. Yeah, great. Don't think that'll be winning any prizes for art anytime soon, but hey, there we go. We can see its binary representation here. Right, so if I change this first pixel to black, this is going to change from a 0 to a 1. Right, if I change it back to white again, you can so down here you should be able to see this pixel changing as I change the colour. So that's a 1-bit image, right? And we can have up to how many colours? 2, right? Because that 1 binary digit can be either 0 or 1, right? Hopefully you've got that. If you haven't, do not past this section. Just go back in the video, play it again, make sure you understand 1-bit images before we move on. So if we want to represent more colors, guess what we need more of? Bits, of course. So we need to know that each pixel has a specific color represented by a specific binary code. So at the moment we just dealt with a black and white image, but we'll look at, as we move on, we'll look at colors. Given a bit depth, calculate how many colors a pixel in a bitmap can be. So that's what we're going to do. So we have established so far a 1-bit image, i.e. we use 1 binary digit, so 1-bit image we can use either black or white, right? So with a 2-bit image, how many colors do you think we can represent with a 2-bit image? Now if you didn't think about that, you might have just said 2, but it's not actually 2, it's 4, right? Because with 2 binary digits we can go 00, 01, 10, or 11. Right, so with 2 binary digits we can represent up to 4 different colours. Now quite what those colours are, it doesn't really matter. Right, again they're just here for sake of example. So here's a 2-bit image, looks a bit like the German flag, although I'm not sure if the colours are in the right order. Perhaps you'll let me know. So this image using this colour scheme up here is going to be represented by white, so 00, 00, 00, 00, 00, 00, 00, 00, 00. Black is 01 in this one, so 01, 01, 01. Back to white, 00, 00, 00. Red, 10, 10, 10. White, 00, 00. Yellow, 11, 11, 11. White, 00, 00, 00, 00, 00, 00, 00, 00. I probably didn't need to do that, but there again, I just did it anyway. Okay, so again, we can use this tool to look at different bit depths. So if I change this to 2 bits, you can now see we've got 4 colors. Right, now you probably can also tell that the number of bits that we're using has also increased. So if I change this first pixel here, what's going to happen at the start? Right, I'm going to change this to red. What's going to happen to these 2 digits here? Yeah, they're going to change to 1, 1 because we're using 2 bits per pixel. So back to this, let's have a look at bit depth and how many colors we can represent. So a 1-bit image, right, where we use either a 0 or 1, we can represent up to 2 colors. For a 2-bit image, like the flag that we just looked at, we can represent up to 4 colors. So it's just 2 to the power of 2. 3, bit depth of 3, we do 2 to the power of 3. So 2 times 2 times 2 is 8. So we can have up to 8 colors with 3 bits. With 4 bits, 2 to the power of 4, up to 16 colors, and so on. Right? So if I say we've got an 8-bit image, I know you've probably just looked at the screen and say, yeah, it's 256, but to work it out, we just do 2 to the power of 8. And you can probably tell that these calculations are not correct because there's I'm missing a times 2 here and a times 2 and a times 2 for this one. Never mind, I'll go back and change it later. What is the maximum number of colors that can be used in a 4-bit image? Can you do that? I.e., what is 2 to the power of 4? So 2 times 2 times 2 times 2 is 16 colors. Hopefully you got that. So slightly trickier question here. A bitmap image includes 7 different colors. What is the smallest bit depth that can be used for the image? So if it's a 4-bit image, we do 2 times 2 times 2 times 2, 16 colors. If it's a 3-bit image, 2 times 2 times 2, we can have up to 8 colors. If it's a 2-bit image, 2 times 2 is 4, so it's not enough colors. So you should be able to work out that we need 3 bits, 2 to the power of 3. We can have up to 8 colors, right? You can't have 2.5 bits, right? It's either 2 or 3 or 4. You can't have half a bit. So a similar question here. So it should be a bitmap, not an bitmap. A bitmap image includes 20 different colors. What is the smallest bit depth that can be used for the image? So 2 to the power of 4 is 16. 2 to the power of 5 is 32. So it's got to be 5 bits. Of course, if we use 6 bits, it would just be too many. It would be a waste of storage space. So hopefully you know that each pixel has a specific color represented by a specific binary code, and that given a bit depth, you can calculate how many colors that pixel could possibly be. Let's take a little break from this and look at metadata for a moment. So metadata simply means data about data. Right, now this doesn't just apply to images, this applies to other files as well. So for example, a web page. In a web page you'll find metadata, which is data about the web page itself. In an image you'll find metadata, which is data about the image. So in this case we have got the height, the width and the bit depth. All of this is stored in the image. So here's some metadata from an image file. It tells us its width, its height, its resolution and bit depth. But width, height and bit depth, they are really important. It's important that you learn those 3 bits of metadata which we can find in an image. Now we can also store additional metadata in an image. So for example, in the case of a digital camera, it might store, along with the photograph that we take, the type of camera that was used, the lens setting, whether or not the flash was on or not. But for GCSE, we need to know that metadata in an image includes these 3 bits of data here: height, width, and bit depth. So the odd one out from this list is, memory size, right? So essential metadata is the height, width, and the bit depth. So moving on to, I've called it color depth here, but color depth and bit depth means the same, essentially. So the bit depth is the number of bits which are used per pixel to represent each color. Right, so going down to this this diagram, if it's 24 bits per pixel, it's 2 to the power of 24, which means we can represent up to 16.8 million different colors. So to help demonstrate bit depth, I've got an image here. I don't know if you can tell what it is. You probably can just about. So it's the resolution is 520 by 362 pixels, and at the moment it's 1 bit, so it's using 1 bit per pixel, which means that the file size is nice and small. But guess what's going to happen when we increase the bit depth? We can represent more colors, but the file size also goes up as well. So that's with 4 bits. This is with 8 bits. Again, we can represent more colors, but the file size is bigger. 16 bits, I don't know if you can tell the difference with video encoding and so on, but again, there's a little bit more detail in here. We can represent more colors, but the file size has gone up quite considerably. So the color depth, aka bit depth, is the number of pixels that we are using, the number of bits that we are using to represent each pixel. So to see if you've got that, let's have a look at these questions. Up to how many colors can be represented when using 16 bits per pixel? We do 2 to the power of 16, which is 65,536. You probably didn't do that in your head. You're not going to get a question like that in the exam because you're not allowed a calculator in the exam. But you might get a question that says how many colors can be represented when we use 2 bits per pixel. So we do 2 to the power of 2, which is 4. Finish this sentence. In terms of storage, the higher the bit depth, the more what? The more storage space will be needed. And in terms of color capability, the higher the bit depth, the more colors can be stored or displayed. So there's a little bit down here about representing images using hex codes. So instead of looking at binary, it looks at hex codes. You don't need to know this for the course, but it's quite good fun. So you might want to have a little play around with that. Let's quickly finish off by looking at resolution. So resolution, which I've previously mentioned, is the total number of pixels used in the image. Right. So here this was a small image on the left. I've just dragged it to made it really, really big, and you can tell that this has a lower resolution, i.e. there's not so many pixels in this image, or not so much data about the pixels in the image, to be a little bit more precise. So there's not a lot of detail in here. This one is obviously a higher resolution image because there's more detail, so it's going to take up more storage space as well. So looking at our objective, what's the effect on file size and quality when you change the resolution? Well, the file size is going to increase, and hopefully the quality is going to increase as well. So an icon image is 50 pixels by 50 pixels and uses a bit depth of 8. How much storage space does this icon need? So we do 50 times 50, which is 2,500. Multiply that by 8, we get 20,000 bits because we're using 8 bits per pixel. So 20,000 bits. Now we should really answer using an appropriate unit of storage. So there's how many bits in the bytes? 8. So 20,000 divided by 8 is 2,500. So 2,500 bytes. Divide that by 1,000 to get the answer in kilobytes. So it's going to be 2.5 kilobytes. The next question here, we're not likely to get this in an exam, but it will get you thinking. So a digital camera. So I imagine the camera on, if you've got a smartphone, I imagine the camera on that is going to be at least 16 megapixels. Do you know what a megapixel is? A megapixel means 1,000,000 pixels. Right, but here we've got a 24 megapixel camera, which is approximately, it says precisely here. So it uses 6,000 by 4,000 pixels, 6,000 across in width, 4,000 high, and uses 24 bits per pixel to store the image. How much storage space does the uncompressed bitmap image require? What do you think? Have a little guess. Are we talking kilobytes, megabytes, gigabytes? What do you think? Well, the answer, we can work out the bits first. So the width times the height times the bit depth is this number of bits. Divided by 8, get the answer in bytes. Divided by 1,000, get the answer in kilobytes. Divided by 1,000, again, we get the answer in megabytes. So 72 megabytes, which is quite huge. But actually, when your digital camera saves a file, it uses a form of compression. But we'll look at that in another lesson. So have a look through these, do the quizzes, have a look at the flashcards too, and if you've got any questions about this section, then let me know.